Alright, in this video we're going to talk about section 1-2, dealing with explorations with patterns. And in this video we're going to find patterns and determine if a pattern holds. Also we'll use deductive and inductive reasoning. Also we'll identify different types of sequences such as arithmetic, geometric, and Fibonacci. Also we'll find the end term of certain sequences and use differences to find a pattern for neither arithmetic nor geometric sequences. All right, so we'll start off by looking at this particular pattern. Okay, and we want to describe that pattern seen in the following that you see right here. Like 1 plus 0 times 9, that does equal to 1. 2 plus 1 times 9 equals 11. 3 plus 12 times 9 equals 111. 4 plus 123 times 9 equals 1,111. 5 plus 1,234 times 9 will be 11,111. If you notice, the numbers in the middle are products of two numbers, the second of which is 9. So here, the products of two numbers, the second of that is going to be 9. The first number in the first product is 0. After that, the first number is formed using natural numbers and including one more in each successive line. Starts at 0, then 1, then 1, 2, 1, 2, 3, and then 1, 2, 3, 4. So the resulting numbers on the right are formed using ones and including an additional one in each successive line. Okay. So do the patterns continue? Well, it may for this case, but in general, it's not going to continue. An example of that would be something like this right here. Notice that 13 times, and then you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2 times 9 ends up being this. Here, the pattern breaks down when the pattern of digits and the number being multiplied by 9 contains previously used digits. Okay, so that pattern is not always going to be true because it breaks down at a certain point. All right, now let's look at two types of reasoning. One of them is going to be inductive reasoning. And in inductive reasoning, you're going to make generalizations based on observations and patterns. Okay. Now, this might lead to a conjecture, which is a statement that is thought to be true, but hasn't been proved. And also, we can take a statement and prove it to be false by coming up with a counterexample. Okay. Conjectures can be proven false by coming up with a counterexample. All you need is a statement or an example that contradicts that conjecture. Right? Now, there are some dangers of making a conjecture. Like in this case, let's say we want to choose points on a circle and connect them to form distinct, non-overlapping regions. In this figure, 2 points determine 2 regions, as you can see here in this figure. You got 2 points on the circle, connect those points, you'll come up with a line segment, and you have 2 regions, as you can see. And then next, if we have 3 points, you connect those 3 points, you're going to have 4 regions. And then 4 points, connect all the points in every possible way, you're going to end up with 8 regions. So it does appear that each time we increase the number of points by 1, we double the number of regions. If this were true, then 5 points would have 2 times the number of regions with 4 points, or 2 times 8, which is 16, or 2 to the 4th. And then if we base our conjecture on this pattern, we might believe that for 10 points on the circle, we will have 2 to the 9th, or 512 regions. Okay. Now, an initial check for this conjecture is to see whether we obtain 16 points or 16 regions from 5 points. And in this case, if you look at it, we do. We have 16 regions from 5 points if you were to connect all the dots in every possible way. Now, let's look at 6 points. The pattern predicts that the number of regions would be 32. But if you look at this very carefully, you're going to see only 31 regions by connecting all the dots in every possible way. You only get 31 regions. So that conjecture in this case is not true. So this is just a situation where we can come up with a counter example by coming up with an example that will prove that the conjecture is false. Okay. All right, next we'll look at sequences, mainly arithmetic and geometric and Fibonacci sequences. Let's define what a sequence is. It is an ordered arrangement of numbers, figures, or objects. Okay. And we can classify sequences by their properties. Okay. Now, a sequence in which each successive term is obtained from the previous term by addition or subtraction of a fixed number, which is, of course, the difference, sometimes called the common difference. So the sequence 2, 5, 8, 11, 14, and so on is an arithmetic sequence, for example. And that's because the difference between each term is 3. As you can see here, if I add 3 to the 2, you'll get 5. 5 added to the 3, you'll get 8. 8 added to the 3, you'll get 11. 11 added to the 3, you'll get 14, and so on. Now, an example would be the number of matchsticks required to continue the pattern. Okay. So if we look at this first figure has only 4 matchsticks. The second one has 3, 4, 5, 6, 7. This next one has 4, 5, 6, 7, 8, 9, 10 matchsticks. This one has 5, 6, 7, 8, 9, 10, 11, 12, 13. So there is a numerical pattern. So what we're doing here is adding 3 more matchsticks in this arrangement. So here the numerical pattern would be this: 4, 7, 10, 13, then 16, 19. And this is an arithmetic sequence with a difference of 3. Because if we look at it, we're adding 3 matchsticks in this particular arrangement. So let's look at an example like find the first 4 terms of the sequence given by a sub n equals to 4n plus 3, and determine whether the sequence seems to be arithmetic. Okay. Now, what I would like to do here is just create a table. The first 4 terms that be n will be equal to 1, 2, 3, and then 4. And then we'll find out what a sub n is. And here a sub n is given to be 4n plus 3. So basically, we're just going to substitute the n with these values here. So if n is 1 in this case, that would mean that a sub 1 is equal to 4 times n, which is 1, plus 3. So 4 times 1 would be 4. 4 plus 3 is 7. So the first term would be 7. And then a sub 2, that would be 4 times n, which is 2, plus 3. 4 times 2 would be 8. 8 plus 3 would be 11. And then for a sub 3, n is 3, so it'd be 4 times 3 plus 3. 4 times 3 will be 12. 12 plus 3 would be 15. And then finally, for n is equal to 4, a sub 4 would be 4 times 4 plus 3. 4 times 4 would be 16. 16 plus 3 would be 19. So pretty much you can see here, this is an arithmetic sequence, because from 7 to 11, that difference is 4. From 11 to 15, that's also a difference of 4. And from 15 to 19, that difference is 4. And another example would be the first 4 terms of the sequence given by a sub n equal to n squared minus 1. And we want to determine whether that sequence seems to be arithmetic. Okay, so the first, let's see, n will be 1, 2, 3, and 4. And then a sub n would be here. Now, n is going to be 1, so that means the first term, a sub 1, would be 1 squared minus 1. Now, 1 squared is the same as 1 times 1, which is 1, and 1 minus 1 is 0. N will be 2. So a sub 2 will be 2 squared minus 1. Well, 2 squared means 2 times 2, which is 4. 4 minus 1 is 3. And now for n is 3, that means a sub 3 will be 3 squared minus 1. Now 3 squared means 3 times 3, which is 9. 9 minus the 1 is 8. And then for n is 4, that means a sub 4 would be 4 squared minus 1. 4 squared is 16, because 4 squared is 4 times 4, which is 16. 16 minus 1 is 15. Let me go ahead and fill in these numbers. Now, does this seem to be arithmetic? The answer there would be no, because notice here from 0 to 3, that common difference is 3. But when you go from 3 to 8, that common difference is 5. It's not the same. Okay, for it to be a sequence, the common difference has to be the same, has to be consistent. Here it's not. Because from 3 to 8, 0 to 3 is 3, 3 to 8 would be 5, 8 to 15 would be 7. So this is not arithmetic. Whereas in this previous example, it is arithmetic. Okay. All right, next, here's the general equation for the nth term of any arithmetic sequence. All right, the nth term of any arithmetic sequence is going to be found by using this formula. A sub n equaling to a sub 1 plus n times 1 in parentheses multiplied by d. Here, the nth term would be a sub n. The first term will be a sub 1, and your d is going to be the common difference. Okay, that's the common difference there for d. Now, let's apply that formula to this example, which is this. A theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. The last row has 144 seats. How many rows are there in the theater? Okay, so in this case here, the first row has 120 seats. That's what A sub 1 is. There are 4 additional seats in each consecutive row. That means your common difference, that's a D, that's going to be 4. And of course, the last row has 144 seats. Okay, and we want to find out how many rows are there in the theater. And in case, that's going to be your A sub n, which is 144. So here we're going to use this formula right here. A sub n equals A sub 1 plus n minus 1 times D, the common difference. So A sub n in this case will be 144, so that's going to be 144. That's going to be equal to A sub 1, that's 20, plus n is the number of seats we're trying, or the number of rows we're trying to find, minus 1 times D, which is going to be 4. So here we have an algebraic equation that we're going to try to solve for n. Okay, so I'm going to bring down the 144, and that's equal to 20 plus, if I use what they call the distributive property, I can multiply 4 times the n, that will be 4n, minus 4 times 1, which is 4. Now, if I combine like terms here, 20 minus 4, that will be 16. So I have 144 is equal to 16 times 4n. And then to get 4n by itself, I need to subtract 16 on both sides of this equation. So that means I'm going to have 128. That will be equal to 4n. Divide both sides by 4. 128 divided by 4 does equal to 32. So that means in the theater, there are 32 rows. Okay. So that's how we solve this equation. And in this case, we have to do this algebraically, finding the number of rows, which is, of course, n. Okay, here's a homework example similar to that. Well, not similar to the one I just did, but it's similar to the one that's in my math lab homework. The school population for a certain school is predicted to increase by 40 students per year for the next 14 years. If the current enrollment is 1,000 students, what will the enrollment be after 14 years? Okay, so in this case here, he's going to increase by 40 students per year, so that's your common difference. D is equal to 40 for the next 14 years. So we have to include the enrollment for this year plus the next 14 years. So n has to be 14 plus 1, which will be 15. And also, the current enrollment, that's A sub 1, is 1,000. So here we're going to use that formula. A sub n is equal to A sub 1 plus the quantity n minus 1 times D. And then substitute those values in that formula here. All right, so N is 15, so we're going to be looking for A sub 15. And that's equal to A sub 1, which is 1,000, plus N, which is 15, so it'll be 15 minus 1 times D, which is 40. Well, 15 minus 1 will be 14. So we have 1,000 plus 14 times 40. Well, 14 times 40 will be 560, because I know 14 times 4 is 56. So 14 times 40 will be 560. And then if you add 1,000 to the 560, you'll get, in this case, 1560. So after 14 years, the enrollment will be 1,560 students at a particular school. Okay, so that's how we use that formula to find this the number of students after 14 years. Okay, here's another homework example. Joe's annual income has been increasing each year by the same dollar amount. The first year, his income was $23,700. And the ninth year, his income was $29,300. In which year was his income $30,700? Okay, so I know what A sub 1 is, $23,700. And I also know this, A sub 9, that's the ninth year, that was $29,300. So we need to find out what that common difference is going to be. Okay, we can use that formula, A sub n equal to A sub 1 plus n minus 1 times d. So this time we're looking for the common difference. All right, we know what A sub 9 is. That would be A sub 1 plus, let's see, n is 9 minus 1 times d. A sub 9, that's $29,300. And that's equal to A sub 1, which was $23,700, plus, if I do 9 minus 1, that would be 8 times d. And now to get 8d by itself, I'm adding $23,700, so I need to subtract $23,700 on both sides of this equation. So here we'll have 8d by itself, 23,700 from the 29,300, that would be that'd be 5,600, and then divide both sides by 8 to solve for d. So here d will be equal to, of course, $700. So the common difference is $700, and what that means here is his annual income has increased by $700 each year. And we want to find out in which year was his annual income, which year was his income $30,700. Well, the ninth year we know was $29,300. So by the 10th year, A sub 10, we just add 700 to that 29,300. And that would give us, and I'll just write this out so you'll see how I'm getting this, $30,000. And then, let's say the 11th year, we add another $700. That would be $30,700. So, in which year was his annual income $30,700, the 11th year. So the 11th year, his annual income was $30,700. Okay. All right. The next sequence we'll look at is a Fibonacci sequence. Okay. Now, a Fibonacci sequence, by definition, is going to be this: f sub n is equal to f sub n minus 1 plus f sub n minus 2, where n is equal to 3, 4, 5, and so on. Okay. And this is how the Fibonacci sequence starts. You start off with two numbers. The next number will be the sum of the two previous numbers. So like, to get this next number, it'll be 1 plus 1, that will be 2. The next number will be 2 plus 1, which is 3. The next number will be 3 plus 2, which is 5, and so on. Okay? To get the next number, you take the sum of the two previous numbers that come before it. All right, so a Fibonacci type sequence is a sequence in which the first two terms are arbitrary, in which every term starting from the third is the sum of the two previous terms, as I mentioned. Each of the following is a Fibonacci type sequence. In each part, you want to find the missing terms. All right, so if you look at part A, we do have this. We do have a 1 and a 1. I can find the numbers to the right of that. So that 1 plus the 1 would be 2. And then to find this next number, we add 1 plus 2, the two numbers that come before it. 2 plus 1, that would be 3. To get the next number, I'll add the two previous numbers, 2 plus 3, which is 5. And then to get the next number, add the two previous numbers, 3 plus 5, which is 8. All right, now we have to look at what are the two numbers that came before this 1 right here. Well, let's think about this. These two numbers had to add up to 1. But to get this 1 right here, I had to add 1 plus some number. What number plus 1 would give me 1? Has to be 0. Has to be. And for this to be a 1, it has to be the sum of these two numbers here. 0 plus what number gives me 1? This number had to be 1. Okay. So that's the whole Fibonacci type sequence here. All right, now look at part B. I need to find out what these three numbers were before the 10 and this number after the 13. Well, this one I can find easily because it's the sum of these two previous numbers here. If I add 10 and 13 together, that would be 23. All right, now let's find out what this number was, because this number plus that 10 gave me 13. What number plus 10 gives me 13? It must be the 3. And then to find out what this number is, this number plus the 3 had to give me 10. So 3 plus what number gave me 10? This number had to be 7. And now, this number right here, this number plus 7 gave me 3. Now, we kind of not talked about this before, but let's let this be x plus some number 7 gives me 3. If I solve for x by subtracting 7, this will be -4. Now, later on, when we get into chapter 5, we'll talk about negative numbers here. Okay? But that's what that entire Fibonacci type sequence is. Okay? Now, part C. This one's easy because we got the first two numbers here. We can find the remaining numbers here. So to get this number, we'll add 2 plus 0, which is 2. To get the next number, 2 plus 2 would be 4. To get this next number, 2 plus 4, that's 6. To get this next number, 6 plus 4, 10. To get the next number, 6 plus 10, 16. And finally, to get the last number, 10 plus 16, 26. Okay. All right. Next, we'll look at a geometric sequence. A sequence in which each successive term is obtained from the previous term by multiplying by a fixed number or a fixed non-zero number, which is called the ratio. That's a geometric sequence. And here's an example of that. Let's say we have 2, 6, 18, 54, 162, and so on. This is an example of a geometric sequence, and that's because the ratio between each term is 3. So for 2, if I multiply that by 3, that would be 6. Take that 6 multiplied by another 3, that'll be 18. Times another 3, that's 54. 54 times another 3, 162. Okay. Now here's a general form for finding the nth term of a geometric sequence. And that's this: a sub n is equal to a sub 1 multiplied by r raised to the n minus 1 power. And in this case, your a sub n, that's going to be the nth term. A sub 1 is always the first term. R is represented by the common ratio. Common ratio is what we're looking for, is what we have here. All right, so this brings up the notion of defining a to the power of n. And that's this: if n is a natural number, that means that a sub n will be equal to this, because a will be used as a factor n times. So if I have something like, let's say, 6 to the 5th power, this does not mean 6 times 5. That means 6 is raised to the 5th power. That means 6 is used as a factor 5 times. And it'll be written like this. Now, if n is equal to 0, and a, which is the base, not equal to 0, then a to the power of 0 is going to be 1. So for something like 6 to the 0 power, that's going to be 1. So in other words, any non-zero base raised to a power will always be 1. Okay. Now, there are other sequences out there as well in mathematics. One of them is using figurative numbers. Those are sequences of numbers that can be represented by dots arranged in the shape of geometric figures. In this case here, we have triangular numbers. Here, those dots are in the shape of a triangle. We start off with one dot, that's 1. And then the next one has 3 in the shape of a triangle. Then 6 dots are in the shape of a triangle. And then 10 dots in the shape of a triangle. Okay. So you can see here that this bottom row of dots are increasing by 1. Same holds true for square numbers as well. He's only got 1 dot here and then 4 dots. That means 2 rows of 2 dots. And then 3 rows of 3 dots. 4 rows of 4 dots. Okay. All right, now here's an example of another type of sequence here. Here we're going to use differences to find a pattern. Then, assuming that the pattern discovered continues, find that 7th term in the sequence. Okay. So we start with this first row right here. We got 5, 6, 14, 29, 51, and then 80. So here we want to find out what this number was or is. But notice on the bottom row you have 7s here. So we know has to be a 7 as well. So that first difference in the arithmetic sequence with a difference of 7. So that means here the sixth term in this row right here is going to be 29 plus 7. Because if you notice here, 1 and 8 has a difference of 7. 8 and 15 has a difference of 7. 15 and 22 has a difference of 7. 22 and 29 has a difference of 7. So that means these two numbers have to have a difference of 7. So if I add that 7 to this 29, I'm going to have 36. And then if we look up here, this number has to be the difference of 80 and whatever this number is has to be 36. So if I add this 36 to the 80, you'll get 116. Okay, so the seventh term in the original sequence would give you 116. All right, on the next page, we're going to look at just a few homework examples to round out this video. In each of the following, list 3 terms that continue the arithmetic or geometric sequence. Identify the sequences as arithmetic or geometric. So in part A, we got 110, 19, 28, and 37. And we want the next 3 terms. Well, let's look at this here. Between 1 and 10, that difference is 9. From 10 to 19, that's a difference of 9. From 19 to 28, that's a difference of 9. From 28 to 37, that's a difference of 9. So that means we have an arithmetic sequence because we're adding the same number each time. So if we want the next 3 terms, we're going to add 9 to the 37. That would give us 46. Add 9 to the 46, you'll get 55. Add 55 to the 9. Well, add 9 to the 55, you'll get 64. Okay. So here, this is an arithmetic sequence because we're adding 9 each time. Now, part D is 2, 6, 18, 54, 162. And then we want the next 3 terms in that sequence. All right, so let's find the pattern here. From 2 to 6, we're multiplying by 3. From 6 to 18, we're multiplying by 3. From 18 to 54, we'll have to multiply by 3. From 54 to 162, we're multiplying by 3. So here we're multiplying the same number each time. So that tells me I have a geometric sequence. So in this case here, I'm going to be multiplying by 3 each time to get the next 3 terms. So if that last term is 162, multiply that by 3, you'll get 486. To get the next term, multiply 486 by 3, you'll get 1458. And then multiply by 3 again, you'll get 4,374. Okay. And part C is 11, 16, 21, 26, 31. And we want the next three terms that follow. Well, from 11 to 16, I'm adding 5. From 16 to 21, I'm adding 5. 21 to 26, I'm adding 5. 26 to 31, I'm adding 5s. So that tells me I have a arithmetic sequence. I'm adding the same number each time. So to get the next three numbers, I'll add 5 to the 31. That would give me 36. Add 5 to the 36, that would be 41. Add 5 to the 41, be 46. So those are the next three numbers in that arithmetic sequence. Okay. All right, so the next example looks like this. Here we want to find the first 5 terms in sequences with the following nth terms. The first 5 terms. So in part A, I got 2n squared plus 6. So I'll list n being from 1 to 5. And then this is 2n squared plus 6. What that means here is this. I take the value of n, square it, multiply it by 2, add 6 to it. So if n is 1, this means I'm going to have 2 times 1 squared plus 6. 1 squared will be 1 times the 2 will be 2. 2 plus 6 is 8. And then for n is 2, this will be 2 times 2 squared plus 6. Well, 2 to the second is 2 times 2, that's 4. 4 times this 2 in front will be 8. 8 plus the 6 will be 14. And then for n is 3. That'd be 2 times 3 squared, 2 times 3 squared, and then plus 6. Square the 3 first, you'll get 9. 9 times the 2 in front will be 18. 18 plus 6 will be 24. And for n is 4, just substitute the n with 4. 4 squared will be 4 times 4, which is 16 times the 2 in front, will be 32. 32 plus 6 will be 38. And then for n is 5, you have 2 times 5 squared plus 6. 5 squared is 5 times 5, that's 25. 25 times the 2 in front will be 50. 50 plus 6 would be 56. Okay. So these are the first 5 terms of this sequence, which is, of course, 2n squared plus 6. Okay. The B part is 5n plus 3. Looking for the first 5 terms, so n will be 1, 2, 3, 4, and 5. And we just substitute each n, the n with those values. So for n is 1, be 5 times 1 plus 3. Well, 5 times 1 will be 5. 5 plus 3, which will be 8. N is 2, so it'll be 5 times 2 plus 3. 5 times 2 will be 10. 10 plus 3 will be 13. N is 3. 5 times n. Well, 5 times 3 plus 3. 5 times 3 will be 15. 15 plus 3 will be 18. Now with this one, you pretty much can determine what the pattern is. We're going to be adding 5 each time. So for n is 4, 5 times 4 will be 20, plus 3 will be 23. And then finally for n is 5, 5 times 5, that's 25, plus 3 will be 28. Okay. Now for part C, we got 10 to the n minus 6. 10 raised to the n minus 6. And we're looking for the first 5 terms, so n is 5, 1, 2, 3, 4, and 5. Now for n is 1, this is 10 to the first power minus 6. 10 to the first is going to be 10. 10 minus 6 will be 4. N is 2. That's 10 squared minus 6. So here, if you do 10, let me find the exponent here, or just say 10 times 10 minus 1. That would be 99. Or this hat key right here, which will give you, and then you type in the 2, right arrow, then minus 6. 94. Okay, yeah. 10 squared is 100. 100 minus 6 is 94. And then for n is 3, this will be 10 cubed minus 6. So here 10 raised to the third minus 6 would be 994. And then for n is 4, this will be 10 raised to the fourth minus 6. That'd be 9,994. And I'll go ahead and write this out. And with this one, you can notice a pattern here. Because I'm adding a 9 in front each time, I increase the n by 1. So for n is 5, this will be 10 to the fifth minus 1. 99,999. I mean minus 6. Wrong. I'll do it again. 10 to the fourth. I mean fifth. Minus 6. 99,994. So you can pretty much determine a pattern from this one right here in part C. And finally, part D is 2n minus 1 in this example. N would be from 1, 2, 3, 4, and 5. 2n minus 1 would be 2 times the value of n minus 1. So for n is 1, this is 2 times 1, which is 2. 2 minus 1 will be 1. N is 2. 2 times 2, which is 4, minus 1 will be 3. N is 3. 2 times 3 is 6, minus 1, which will be 5. And this also has a pattern here. You're adding 2 each time. So for n is 4, this will be 2 times 4, that's 8 minus 1, which is 7. And then finally for n is 5, 2 times 5 is 10. 10 minus 1 would be 9. So here there's a pattern right here for this sequence. We're adding 2 each time. Okay. And the last example in this video, consider the sequence given in the table below. Find the least number n such that the nth term of the geometric sequence is greater than the corresponding term in the arithmetic sequence. Okay. So this top row represents an arithmetic sequence. That common difference, if you look at it, is going to be from 400 to 900, that's 500. 900 to 1400, that's 500, and so on. In the geometric sequence, the common ratio, if we're going from 3 to 9, we have to multiply by 3. From 9 to 27, we're multiplying by 3, and so on. So here we want to find out the least number n, or the nth term, where the nth term of the geometric sequence is greater than the corresponding arithmetic sequence. Okay. I'm going to look at, let's see what the seventh number is in the arithmetic, and then for geometric, because I want the number in the geometric sequence to be greater than the term in the arithmetic sequence corresponding. All right, so for the seventh term, if the sixth term is 2,900, add 500 to that, it'll be 5,400. Now in the geometric sequence, if this is 729, I'm going to multiply 729 times 3, which is 2,187. So in the seventh term, the geometric sequence is smaller than the arithmetic sequence. Now let's look at the eighth term. Well, that seventh term is 5,400. Add 500 to it, you'll get 5,900. And for the 21, well, if the seventh term of that geometric sequence is 2,187, let's multiply that by 3. You'll get 6,561. Notice right here that the geometric sequence of 6,000, the 6561 in that geometric sequence is greater than the corresponding 5,900 in the arithmetic sequence. So we can say here is at the eighth term, the value of the geometric sequence is greater than the corresponding value of the arithmetic sequence. Okay. Okay. So that does complete this video on section 1.2 dealing with explorations with patterns. Okay. Make sure that you do complete the homework in my math lab, and also feel free to email me or contact me if you have any questions about any of the problems in this video or in the homework.